Another famous model for modeling interest rates is Cox-Ingersoll-Ross model. Now this is exactly the same as Wasicek model. As you can see, the only extra term we add here is square root of xt. So again, in this model, this is the stochastic part. The stochastic part comes from the Brownian motion, which you get from this normal distribution, and t could be as small as you want to, so you can adjust the t in your grid. So the long-term mean is mu, the speed of reversion is theta, and the instantaneous volatility is sigma. Long-term variance is sigma square by 2 theta. This is precisely what we did in Wasicek model. So only extra term is this square root of xt. This is our extra term. So let us go through the model. So again, your drift is this part, theta times mu minus xt. So theta times mu minus x. Diffusion is sigma times square root of x. So I'm raising x to the power of 0.5 right here. So this is the diffusion part. So again, same as the Wasicek model, only thing extra I have added is this term. State variable is x, time variable is t. You have to solve for variable x. Initial value you can take as 0.5. So when I will run, I will take the initial value as 0.15. We are going to simulate model 1. Now you have to give the parameters. So you give to 3 parameters you have to give: theta, mu, and sigma, because xt you will solve anyway, and this dwt is generated by the system. So we are going to give these values: mu is 0.1, sigma is 0.2, theta is 2, and then we are going to plot this value x. So again, I am not using a particular grid here, so we are going to use the standard grid. So in the standard grid, the time is taken as 1 by 100, and you can change this grid. So I have described in previous lectures how to change this grid if you want to change your grid. So here we are just taking the standard grid. So let us now plot it and see how things look in R. So now let us do this in R. So this is the CIR model. So you have this theta, diffusion is x to the power of 0.5, state variable is x, time variable is t. I have taken the initial value as 0.15. Let us just run it. And here you get the Monte Carlo simulation. So you're starting at 0.15. So let's just run it couple of times. So you get another shape of the graph. I'm going to run this again. Get another shape. Just keep running it as many times that those many shapes you will get. So simulation means you have to simulate this 1,000 times and then make probability distributions.